can give you pizza.
Oh yeah.
You all decided to do it?
I never told her. I should tell her.
So I'm talking today, Jeff said. Good job. Okay, so I guess what I want to do is talk about relative trisections and talk about them from a Morse 2 function perspective. Okay, so but I think I never properly talked about Morse 2 functions on four manifolds in general. Relative is going to mean these are on four manifolds with boundary. So, but the Morse 2 function thing first. I think when I did this for it, did I do it in full generality and arbitrary dimensions or just dimension 2? Anyway, I'll remind you quickly. So Morse 2 function on 4 is f r2, which looks locally like one of these models. So either it's just a regular point, so it just looks like a subversion from R4 to R2. So that would be T x y z maps to x. Or so that's a regular point. Or a critical this a fold, so T x y z maps to T still in that thing, and then the second order we have some plus or minus x squared, t squared, and so that's called fold. Those points are folds. And then the last thing that you have to allow is for a cusp, where T x y z maps to T, and then the x coordinate you do x cubed plus or minus, let's see, minus tx plus minus y squared plus minus c squared. And these are just local coordinates. That doesn't matter what they're called. That's a cusp. And if you plot the so the singular set points with neighborhoods like this give the singular set. We can call it Z. And if you think about it, so here, the set of critical points, the points we actually need this model is precisely the set of points where x, y, and z are all 0 in this local model, so it's one-dimensional. So that'll be one-dimensional. Here, the set of singular points is the semi-cubical cusp thing, and so it's one-dimensional, but it has this single point. There's a single cusp point. So Z is a one-manifold in X, and it contains the cusp set C. Cusp set C is contained in Z, and that's a bunch of points. And then the image, so f of Z. right, that kind of cusp that I can draw, it's not so many typical cusp, really should be, it really should be numerically like, same concavity on both sides, but anyway, so it's just some immersed, it's like a Legendre curve. It's just an immersed curve with cusps. Immersed, and possibly many components curve with cusps. And it has, so the inverse image of a regular point, let's see. So think about the topology of what's going on with the four manifold, F inverse of a regular point, of a regular value, I should say. A regular value is the image is something all of these pre-images are regular points as usual. So F inverse of a regular value by standard differential topology theorem, which you might forget, is the surface. Surface. And of course, we have to, whether X has boundary or not determines whether or not the surface has boundary or is a closed surface. And then we want to talk about what I want to study now, just briefly discuss, is what happens when you cross from a fold from one side of a critical point to from one regular point on one side to another. So a good way to say that is if let's say A arc 2 with regular value endpoints. And transverse to A is transverse to F of Z. And this is cusps. So that's an example of one, or I could have drawn a longer one, right? Then then F inverse of A is actually going to be a three manifold. And it's good, if the endpoints are, let's say, the boundary going from Q, let's say, this is A. So you can see that it's a three manifold because one way to see it is I can sort of put a little, box around it, and that will be four-dimensional. That's four-dimensional thing. And then you can say, well, if you put a little, coordinates around it, so I can call it neighborhood, then I can think about this four-dimensional piece that sits over there, and I can think about projection onto the I factor, right? And then I can show that will have no critical points. And then F inverse A is like the inverse image of 0 in there. It has no critical point precisely. It's transverse to the fold, meaning that you have no critical points. The critical, you see critical behavior this direction, but not in this direction. I'm just powering through the details, but that's the idea. So you can see that it's a three manifold, and furthermore, and it's a coordism from F inverse P up from Q. I'm just going to decide to orient A. So from this three manifold, from this surface to that surface, and furthermore, you get. So if I think of this three manifold projecting to A, and I think of A as one, as say R, if I parameterize A, then you get F restricted to F inverse A, and from that three manifold to A. This is a it's a Morse function. It's an honest Morse function. And what you're doing is you're basically, so in the little box right here, if this is one of the fold areas, then in this little coordinate system, T is this direction. That would be T. Or if I was over here, that direction, t direction. And so because you're cutting transversely across these folds, you're really just seeing this behavior locally. And you're missing the cuts altogether. So, so that's a Morse function, and has critical points of various indices. Critical points when you cross folds. And those are all in principle could occur. It would be 0 if you have in that direction, it's plus x squared plus y squared plus c squared. 1 if it's minus x squared plus y squared plus c squared, and so on. So it's indexed of this little quadratic form there. So I often will, when I'm thinking about pictures like this myself, I'll draw a little arrow and I'll draw 1, meaning that's index 1 in that direction. That's not necessarily standard notation, but something. But what's worth thinking about though is that so we can decorate. Well, I'm not writing it down, but if this is index 1 going that way, then what is the index going this way? And those who've seen me say this before many times can't tell the answer. But if you have to think for more than a second to get the answer, then give the answer. It's either 4 minus 1 or 3 minus 1. Which one it is? I set it up so that either now I don't know whether you all don't know or you all know the answer. So anyone can tell us the answer. Now I know the what's that? 2. That's right. It's 2 because this index is the index on a 3-dimensional. Right. So there's that little arrow sitting over there is a little 3-dimensional. And going this way, if that was index 1 going that way, then it's index 3 minus 1 going that way because it's 3-dimensional. It's not, that's the other, the first thing that you have to remember. If it's a Morse function, an ordinary Morse function on 4 hand flips trans down and then you get 4 minus 1. But because this is a local, like 3-dimensional picture, the index switches the other way. So in particular, so what might be happening, for example, well, all sorts of things can happen, but it might be, for example, that here you have the genus 3 surface, the genus 2 surface, later fiber over there, and then you pass an index 1 critical point, you would then get to an index 3 surface because you built a little cobordism from one to the other, which attached the handle. The handle on there, that handle's and going back the other way, you would have an index, a genus 3 surface, and coming down some circle, and collapse into a point that separates across the surface. So that's, yeah, go ahead.
What's the pretty much right on the fold? Like,
right on the fold, it's the singular surface. It will be something like, and you have an intervals worth of those along the fold. Much harder to draw, so pretty much. And I'll explain why in a second.
How did you know it was 1 going that way?
Oh, I just tried to check. I mean, the picture I drew was too random to even. I just figured out what it might look like, right? And it might be next one that way or not. Okay. If it's index 0, then what that means is, if I have a 0 thing out here, that means that, well, maybe, you might not have any image image point here might be empty set, in which case the image image point here would be a sphere. You're creating a 3-dimensional 0 handle, right? As you cross there, you might get disconnected components and so forth. Okay, anything else? All right. The cusp is worth thinking about. So near a cusp, you draw a picture that looks like this. Then we can think about, a good thing to think about is this is the local picture with T going in this direction. What this says, if you think about it, when T is negative, you get x cubed plus x, which is like this, and so you have no critical points. When T is positive, you get x cubed minus x, And with this, we introduce some pair of critical points. And that's this birth of this pair of critical points. So this is zero and local model. And then you get the pair of critical points of current canceling index. So they could either be like 0 and 1, or you could have 1 and 2. Or flip this upside down, 3 to the top, 2 down here. These are basically the two things that can happen. And so in this situation, what after here it's sort of basically what you're going to have is, say you have some surface, that's the genus, and here you have this regular fiber would have an extra 2-sphere component, but that 2-sphere component is immediately reattached to that surface of genus, the original surface again, by some one end attached to it. So this point is as a canceling pair of critical points. So locally, if you draw a little box around your cusp, what you're seeing is a birth of a canceling pair of critical points. So in particular, when you do the 1-2 case, you have to have you're adding a 1 handle, but then it gets canceled by a 2 handle. So if you draw it from this perspective, you might have genus 2, then you have genus 3, and then you get back down to genus 2 again. And the way that happens when you study what's going on here is that you have a birth of a pair of, that creates this extra genus here, and then so you have to have balance where if we can, the best way to sort of understand what's happening is to understand what's happening going this way. So this is index 2 going both directions. So starting from this genus 3 surface, going this way, there's some curve that shrinks down to a point, and going that way, it's got to be a different curve that intersects the transverse 3 points. So that's the curve that compresses going that way, and this is the curve that compresses going that way. So this is just the standard thing for what happens when you have a canceling index 1 and 2 critical point on a 3. But what happens here is that they're both compressed simultaneously, and that's what's hard to really draw. And there's just tons of interesting things to think about just in this picture moment itself. So okay, that's kind of like the big picture background for force 2 functions. I want to now zero in on particularly this class of Morse 2 functions, which create trisections, and then look at them in the case of memorable.
Why the genus is not changing?
Here, well,
No, in that picture.
in this one, why is this still the same as this genus? From here to here? Well, here's one stupid answer, which is that, so I'm looking at the irreducible point there and the irreducible point there. So we were just trying to understand it by looking at an arc going across there. But we could just as well look at an arc going this way. And if I look at an arc going that way, that's a 3-manifold cobordism from this surface to that surface with a Morse function and no critical points. So therefore, it must be a product. And then the same. You have something, if you ever want to, well, here's something I don't fully understand. So you can think about this circle here. And so sitting over that is a 3-manifold. And with a closed 3-manifold with a circle value Morse function with a single index 1 and index 2 constant critical point. And you can state the surface. I feel like this is some standard stuff that I just haven't really quite learned to think about carefully. This is more like a differential geometry or anything like that, a dynamic systems question. You can, so you start with a surface. I want to sort of flow around and come back to where I started. In what sense? Well, what I can do is I can, look at this 3-manifold, look at a metricon or something, get a gradient, I can get a gradient flow. I get a flow that on the 3 manifold that points in this direction. It goes around, except it'll get sucked into, if you start here, you'll eventually there'll be precisely 2 points on there that for which the flow doesn't continue, and you get sucked into this point. So if I want to say flow from here to this, I'll get a map surface to that surface minus a circle. You'll miss a circle because going this way, you get a circle. And then if you keep going, points on that circle will disappear and come back. And I claim that in the end, I think you get a flow, you get a map from this surface minus a little x, I'm not sure, back to itself. And I'd like to know more about the dynamics of it. I mean, it's not a topology question, it's like writing down vector fields. Of course, there's lots of choices to make it work, but I just always wanted to understand that better. I'm going to find a trisecting Morse 2 function. Let's do a closed manifold case first, right? Closed manifold is, I'm just going to show you what is one singular value set. Looks like this. So, there's a big circle of index 0 critical points. Oh, by the way, good exercise. Exercise. Show that. The map. X2, S4 to R2 is a Morse 2 function. And with one circle, with one circle. It looks just like that. That's not hard, that's just, if you want to just get going. So there's one circle, which is sort of an equator, as it were, where it folds, and that's all you see. So that would be what you see if you just saw S4. So I'm going to draw some first. And say I'm going clockwise. That's not part of the singular set. And then the singular set is going to look like, I drew exactly the same picture for, almost exactly the same picture for the surfaces. To the up here, this is a picture from a paper from Kirby. Just some little boxes. That's how you look and go in these boxes in a little bit. Something goes in those boxes. And then here we have that's not supposed to stick out. Okay, so before I tell you what's in the boxes, I'll tell you what that these are all index 1 as you go in. or equivalent index 2 all of them. So what goes in the box is, in the box you just have stuff coming in, stuff coming out, and then it just looks like some 1, 2, 3, 4, 6, 7, 1, 2, 3, 4, 5, 6, 7, and then goes up just. But no cuts, that's the important point. So in other words, no cusps, no backtracking. And actually people now claim, Bicor and Saiki claim that a paper showing that they claim have proved, I did understand their proof once, that you can actually find on any given Morse 2 function. So Robin Kirby and I proved that on any given four manifold, you can find a Morse 2 function whose image of the standard set looks like this. They proved that you can actually have there be no crossing in the boxes. So, what you want to think about is, right, so what you should have now is, the picture you should get from this is, sitting over the central point, there is a surface of some units G. And then, as you walk out along either of these three rays, or almost any ray actually, you walk out along almost any ray of this disk, you will see index 2 critical points. So you'll see some compression, then some other compression, until eventually you get down to the 2 sphere, and then here to 7, and then you're done. So that's what the manifold is sort of somehow swept out by these compressions, which are actually therefore handle bodies. From this, the F inverse. Okay, so from this, F inverse of almost all rays, almost any ray. In particular, all the rays except the ones that go through cusps, right? Almost any ray is a handle body. Filling whose boundary is filling the central surface CG, which is that first of the origin. And I'm assuming this is 0 here. The whole formula sits over there, and that's the picture. And let me think. So say about this. So there is that. There is that such that Morse 2 functions exist. On arbitrary closed oriented four manifolds. Don't ask me about anything. Just haven't thought about it much. And therefore, trisections exist. And this is really how Rob and I originally came about thinking the existence of trisections. There are simpler proofs in the end, but this is the intuition we had. So why, therefore, trisections exist? Well, that takes a little thought. I claim that we sort of see that we have a surface, and we see that the four manifold is split into three pieces, and that the pairwise intersections of the three pieces are handle bodies. I haven't shown you is that each of the three pieces by itself is a four-dimensional one handle body. Maybe we can connect some S1 3s. I'll just try to show you that in a second. Something that isn't written down anywhere, and it's sort of a purely Morse 2 function proof of that fact, like I gave such a Morse 2 function proof, or sketched one for the surface version, saying pull things back and forth. It's a little trickier, like pulling things back and forth and moving stuff around. You start with this random crazy Morse. You'd like to have a proof, you just start with a random crazy Morse 2 function. Those exist, but it's general principles. And then you want to try to clean it up by some kind of grading argument. And once you get getting three, one issue is you want each arc of cusps to have at most one, each arc of folds to have at most one cusp in each of the three sectors. That's not hard because if you have lots of cusps, you can break them up. If you have this, you can use a swallowtail and pull things across. If it's pointing the wrong direction, when the cusp pointing instead of out, and so on. I know there's more index 0 folds than you might hope, and so on. It's complicated. I think it's doable. It's not clear what the payoff would be, except it'd be interesting. I think all the resources are probably in work of Saiki and Whiteboard. But anyway, we thought about it a little bit differently. We sort of started from hand decomposition of 4 manifold and produced this more sticky function. So it's a little bit mix and match. But okay, so why do trisections exist? Why? So I claim that. So if I call these three sectors like A1, A2, and A3, those are subsets of R2, then the claim is that F inverse of AI is a 4-dimensional one-handed. So the way I like to see it is if I draw one of the AIs like this, I can redraw line, redraw, and I'm going to sort of straighten out. Maybe A2 is what I'm focused on. I'm going to redraw it. I wish I put the cusps on the inside. Doesn't actually matter. We can put the cusp on the inside here. So these are indexed. That's index 0, index 1, index 1. These are index 1 going up, index 2 going up. Remember that 1 going this way, this is index 1 going up, and 2. So there's a bunch of different things, and this is just some swirling around stuff. What happens there? So what you want to do is think now, this is a, so I've redrawn that sector with a piece of the 4 manifold xi, and I call this xi. Piece of the 4 manifold projecting on the platform like this, and then I want to further project to the horizontal direction. And then you can calculate that, using the local models for these folds and so forth, you can calculate that you get precisely critical points. You get an honest Morse function with critical points precisely at the vertical tangencies. And those critical points going this way are index 0, 1, 1, and these cusps don't produce any critical points. You get critical points precisely at the vertical tangencies. Again, kind of strangely reminiscent of contact topology. Something happens in vertical tendencies, maybe contact topology, you don't allow them, or you keep track of them as something special. So some topology changes go like vertical tendencies. And so the point is now that format, there are no further critical points, so I'm not going to write this down, but four manifold xi therefore has a Morse function on it with a single index 0 and a bunch of index 1 critical points. You can really think about, you can sort of visualize it better than that in a sense. You've got nothing out here, and then suddenly you get sort of an arc's worth of balls. That's really a ball, right? That's a 4 ball. And then you get an arc's worth of index 1. You know, when you come to here, you've attached a 1 handle. You attach a 3-dimensional 1 handle cross I. So that's really a 4-dimensional 1 handle. And then you just attach a bunch more 4-dimensional 1 handles. And then you might say, well, what happens? What really are these cusps about? Well, one way to think about it then is that the extra information here is that this 3-manifold, which is now essentially the boundary of xi, has a Morse function on it with, if you're going vertically, index 0 critical point, bunch of index 1 critical points, k of them. There's k here, that's k of them there, k index 2 critical points, and then index 3 critical points. And this is actually the standard Hagar splitting. If I split there on that surface, that's the standard Hagar splitting of this boundary 3-manifold. So here, sitting over here, you see a connect sum of, if there's k index 1 critical points, you see a connect sum of k S1 cross S2s. And here you see the genus K surface. And then that splits into 2 halves, which is the standard in genus K splitting. Then when you keep going, you get genus K plus 1. What you've done is you stabilize that. So eventually here what you have is, because you've added an extra canceling pair of 1 and 2 handles. So by the time you get to here, this is this whole thing is the connect sum of k S1 cross S2s with a higher genus than expected Hagar splitting of genus G, where G is another thing there, a genus G Hagar splitting. And that's precisely what these three, remember in the trisection picture, when you put 2 of the handwise together, you're supposed to get a Hagar splitting of connecting some of S1 cross S2s, and but it may not be the trivial one that you start with, it probably isn't. These cusps correspond precisely to stabilization. I guess I wanted to do the cusp after, so you sort of see the one first. It doesn't really matter, but stabilization can happen. Questions? I think having set that up, I think I can do the relative case fairly quickly. That's all of that over there is justifying this, therefore. That's justifying why each piece is the same. So now I want to show you what is relative. I sort of recently decided I like to define relative trisections directly from Morse 2 functions, because the sort of breaking the pieces definition is just really clunky and confusing. So if X has boundary, let's just put a that's a connected boundary. You can do this with disconnected boundary too. Then we're going to require a little bit more. So trisection Morse 2 functions. This Morse 2 function f from x by 2. Okay, so let me tell you the picture I have in my head. I'm going to get rid of this 0 fold. That's not going to be there. It's not going to be closed. There's going to be some boundary sitting here. So I'm going to think of like a solid block of cheese or something projecting on the board. And so there's going to be some boundary here. And there's also going to be top and bottom of this thing. Except top and bottom, this direction is really 2-dimensional. So it's not the endpoints of an interval across from the disk. it's the boundary of the surface across with the disk. So I'm gonna have this picture in my head about the tin can sitting out here, and it's at the two endpoints, the two end caps. That's an S0 across the disk, but really it's a one manifold across the disk. So that might be a whole bunch of circles across the disk right now. Here, it's a whole bunch of solid chloride. So try to write that down. Such that, so the first thing is we should require what happens on the boundary. So F, so first of all, F of X is equal to this. And I'm gonna write down F inverse of the boundary of the unit disk, S1, is contained entirely in the boundary of X. S1 being the boundary of the disk. Okay, and F restricted to F inverse of S1. So F inverse of S1, I want that not to have any critical points. So that's something mapping down. So that is I want that to be is a closed, compact surface bundle. S1. With fibrous surfaces with non-empty boundary. Okay, so we're gonna have a picture that looks just like that, but instead of this ring of zerofold out here, we're going to have just the edge of the four manifold. So there's a circle bundle sitting over here. And fibers, surfaces with non-empty. And there's more, and F inverse of F inverse of the interior of the disk, I think this is the right way to say it, intersected with boundary of X. So if I take interior stuff and I see, that's going to be all kinds of stuff, but I have to take just a part of that, so the interior, that is a disjoint union of interior disks cross as ones, projecting to the interior disk. So I just have a bunch of open solid tori projecting down to the disk. That's like the tin can was at zero, disk cross at zero, but not disk cross at. Maybe a better way to really, I'm not going to write all this down, but a better way to say it is maybe it's best to say that. How about this? The closure of this. Take the inverse image of the interior, intersect it with the boundary of this, then take the closure. That's a bunch of solid tori projecting down onto the factor. I'm going to leave this up here. Get rid of this 0. Colors. Yellow. If you're taking notes, this is not. What did I do in this picture? This is what, and then the rest of the singular set. I want all of the singular set, all of the singular located is the interior of C, interior of X, sorry, and the singular value set looks like this. And so yellow is not fold. When it's singular value set, it looks like the white stuff. And yellow is just the boundary of the disk clock right? Okay, so, and then so that's my definition for a trisection. It's essentially what I had before, except I'm kind of very rigidly specifying on boundary. Well, the first point is that the structure is used on the boundary. Boundary that is an open composition. This word has been thrown around a little bit, maybe not defined. Here's what one way to take it is it's precisely this definition. It's a bunch of solid tori. There's a little bit more. It's a bunch of solid tori and then a circle bundle of complement, such that the pages come in as longitudes of the solid tori. Another way to say it is that so you can see this binding. And F inverse of 0 intersect with boundary X. So F inverse of 0 now, this is going to be a surface with boundary. And its boundary is some disjointing of circles in the three-manifold boundary. And then a typical page, is what I'm going to do is take, if I adopt the notation where R sub theta equals the ray that makes angle theta with the x-axis, right? Then the typical page is we take just simply, all we have to do is take F inverse of R sub theta intersect with the boundary of x. And what you'll see is this stuff here will of course end when you get to R equals 1. So over here, you'll see a surface with boundary. And then filling in, over this part, you'll just see the circle cross interval. So you'll see like a bunch of angle lines. That's the color extension. And then the boundary of the page. So this is a venerable subject. Studying multi-compositions of three manifolds, and it sort of just seems right as the natural structure you look at on the boundary. And then I'll just give you the definition. A relative trisection of a four-manifold boundary is F inverse of, F inverse of A1, F inverse of A2, F inverse of A3, coming from a trisecting those two functions. A decomposition of this form coming from the trisecting force two functions. I mean, that's not the original definition we gave, or that most people throw around. If you can get a Morse 2 function in that form, then the decomposition that produces is what we call a relative trisection. And somehow, to me, that gives more intuition, perhaps, than the standard definition. But let's just think briefly about what's happening. So to think a little bit about what this is some surface of G. Now what you should think is there's some surface of genus G here, and there's some surface of some lower genus here, which I'll call P. It stands for page. Okay. The page really should be thought of as this thing together with these annuli that extend across these rays. Okay. There's a page here, and so sitting over here now, sitting over one of these rays is not a handle body, but a compression body. Where you start sitting over a ray. Well, this is the page, right? But if I look at F inverse of R theta, not intersect with boundary, the entire thing. This is a compression, what's called a compression body. Which means that you have, basically you start with some hygiene surface, 3, and then that would be in the middle, and you cross it with the eye a little bit, so out, and then you start filling in some curves, but maybe only 2 of them or something. And then if you can imagine what this would be, for example, so let's take a picture of the compression body. If I think of the solid object pictured here, which is the solid GS3 handle body with a core drilled out there, that's an example of a compression body. That's a coordism from GS3. Oh, except that, sorry, this is a compression, this has boundary. This doesn't have boundary. So what I should do now is I should, that makes it hard to visualize. Because we should be, this is the out, this would be sigma G on the inside of the thing, and then here, that's the page for one. So for example, this would be a compression body from a once punctured genus 3 surface down to a once punctured genus 1 surface. And we should stop there. I'll say a little bit more. My goal on Friday is to say a little bit more about this. So I'm really just trying to, Jeff and I are just trying to touch on various topics. Say a little bit more about this, maybe answer questions you might have about this. And I would also like to sketch something about group trisections, which is what's the group theory behind what happens when you apply pi 1 function to all the pieces of the trisection. Ask me questions next time. If you have any prepared questions.